I've been putting up these podcasts that are about AI for various purposes, and weather and climate forecast, of course, is one of the main ones. Science and Nature also keep publishing these articles on use of AI and machine learning for weather forecasting because that's a hot topic, and they don't want to be left behind in capturing the most exciting new paper that comes out. So I will follow the same philosophy in terms of just providing brief introductions to these papers from high impact journals because they do provide some idea on where the field is going and what's the state of the art in terms of using AI and ML for weather and climate forecasting. And again, caveat is that I'm not an expert on AI, and most of us will be AI users. I use AI already for downscaling forecasts for various applications and so on, which we have talked about elsewhere. So we'll briefly read this paper that just came out in Nature literally last week that talks about probabilistic weather forecasting with machine learning. What's new about this? Well, let's see. Weather forecasts are fundamentally uncertain, so predicting the range of probable weather scenarios is crucial for important decisions, from warning the public about hazardous weather to planning renewable energy use. So here it is about range of probable weather scenarios. Just a few days, but we are calling them scenarios because, as we always say, Mother Nature can give us one realization of wherever she goes, but we know that starting from somewhere, she could have gone in many directions. And when we do forecasts based on dynamic models or AI, we need to have an idea of the range of solutions she could have produced, because we cannot make just one prediction that's going to exactly match nature every time, right? Those are what we would call scenarios. So the idea here is really to produce ensemble forecasts. Remember, we discussed before that models do ensemble forecasts where you either perturb the initial conditions and integrate multiple times to produce a range of solutions, or you perturb physics. There are some details on how the ensembles can be produced. Keeping all that in mind, traditionally, weather forecasts have been based on numerical weather prediction NWP models, which relies on physics-based simulations of the atmosphere. Recent advances in machine learning-based weather prediction (MLWP) have produced ML-based models with less forecast errors than single NWP simulations. So when typically AML is used, they are comparing with the deterministic component of the NWP, so take one ensemble member and look at that. However, these advances have focused primarily on single deterministic forecasts that fail to represent uncertainty and estimate risk. Overall, MLWP has remained less accurate and reliable than state-of-the-art NWP ensemble forecasts. This is a key difference here. Okay, here we introduce GenCast, a probabilistic weather model with greater skill and speed than the top operational medium range weather forecasts in the world, ENS, the ensemble forecast of the European Centre for Medium Range Weather Forecasts, or ECMWF. GenCast is an ML weather prediction method trained on decades of reanalysis data. You know already, reanalysis is a mix of data and a model that produces gridded dynamically interpolated data for the past. And people always argue that when you use reanalysis and try these forecast or hindcast experiments, there is artificial skill, because in the real world you are doing the forecasts by initializing data simulated product. Now that is analysis and not a reanalysis. Some details there, but just keep in mind. GenCast generates an ensemble of stochastic 15-day global forecasts at 12-hour steps and a quarter of a degree latitude longitude resolution for more than 80 surface and atmospheric variables in 8 minutes. That's a remarkable speed with which forecasts are being produced for 15 days and ensembles. Okay, it has great skill greater skill than ENS on 97.2% of the 1,320 targets we evaluated, and better predicts extreme weather, tropical cyclone tracks, and wind power production. This work helps open the next chapter in operational weather forecasting, in which crucial weather-dependent decisions are made more accurately and efficiently. So we looked at GraphCast, which was doing the former of making forecasts and comparing against NWP's deterministic. Deterministic basically means one realization and you think that's going to be reality, whereas when you do ensembles you are giving a probabilistic forecast. That's the difference between deterministic and probabilistic. Okay, I'm going to skip ahead lots of details, technical details of course, which I'm going to skip, and there are examples of each of these forecasts, tropical cyclones and so on, that I'm going to skip as well, and we'll just jump to summary after this methodology schematic here. So here is GenCast, and this is a diffusion solver step. In each green box there are things, and there is the globe, and there is the time going from x0 starting from x minus 1, x1 is produced from x0 and so on out to xt, and this shows a schematic of how GenCast produces a forecast. The blue box here shows how conditioning on inputs x0 and x minus 1 time steps an initial noise sample z01, so z01 is here, is refined by the neural network refinement function r theta in the green box, which is parameterized by theta. The resulting z1 is the first refined Z11 is here, is the first refined candidate state, and this process repeats n times, going here to Z1n to move from x0 to x1. Okay, so just follow. I'm being very brief, of course. You can read the details in the paper if you're an expert. Otherwise, you think at my level. I read it, I understand most of it, but I don't want to start explaining technical details and get into trouble. Okay, so idea of these podcasts is just to give you an introduction of what is happening right now. So the final Z1n is then added as a residual to x0 to produce the weather state at the next step x1. So you come out here, this is the forecast. This is the GenCast, and this is the forecast from x0 to x1. Okay, and this process then repeats auto-regressively for t equal to 30 times, conditioning on xt and xt minus 1, and using a new initial noise sample zt0 at each step. Okay, here you can see z20 out to zt0. Okay, that's how you are coming back to go forward. At each step to produce the full weather trajectory sample. For visual clarity, we illustrate the previous state in parenthesis here as xt minus 1 and so on. Below the current state xt, note that this it is not added to ztn as a residual for predicting xt plus 1. Each trajectory generated by independent z01 t 1 to t noise samples represent a sample from p probability of x 1 to t being dependent on x0 and given x minus 1. Okay, so you get the idea that they are trying to produce an ensemble, and they're doing this purely using data and this methodology, whereas in the models you perturb initial conditions, or sometimes you do perturbed physics ensembles and so on, but the details are not that important here, just to see that this has found a AI ML way of producing ensemble forecasts, and still do it much faster, so that weather scenario is given and not just a deterministic realization, because the uncertainty on deterministic realizations is always, it just tells you tomorrow it could be so much rain or such a temperature without saying what the potential range is, so people can get used to the probability and make probabilistic decisions. For example, people can understand when the weatherman says or weatherwoman says there is a 30% chance of rain tomorrow, or that it'll be partly sunny or partly cloudy, and so on and so forth. So people are used to looking at it and deciding what to do with that information, and you need, that's for people, but farmers need a more nuanced decision, airlines, whoever else. Okay, so with that brief mention of the method, let's read what the conclusion is. Our results indicate that probabilistic weather forecasts based on MLWP can be more skillful and faster to generate than the top NWP based ensemble forecast ENS of ECMWF. So I've skipped the details on sorry about that. I got my system crashed. Every time Microsoft updates the software, the operating system, this particular software that I'm using, Panopto, crashes. So there is some crosstalk that they don't like each other so much in this mode. Oops, I already have. Okay, so we're talking about the conclusion and how the GenCast is doing better than ECMWF's ensemble forecast system. That's the key message here, that this is using AIML, purely data-based AIML, to do ensemble forecasts as opposed to deterministic forecasts that other AIML methods have reported so far. GenCast succeeds across three key desiderata for probabilistic weather models. First, GenCast generates ensembles of sharp individual weather trajectories with realistic power spectra rather than sets of summary statistics such as conditional means. That's the details of statistics on how you determine whether the ensemble is covering the reality, or how it depicts the weather itself. If weather went somewhere and you have probabilistic distribution around it, whether from models or AI, how do you make sure that your ensemble is always realistic around the one realization that Mother Nature keeps giving? Second, the marginal forecast distributions of GenCast, that is forecasts for a given place and time, are well calibrated and provide more skillful predictions than those of ENS, including better predictions of extreme events. Third, GenCast outperforms ENS across several evaluations that require capturing spatial and temporal dependencies in the joint distribution, pooled evaluation, regional wind power forecasting, and tropical cyclone track prediction. Again, I want to remind you of the caveat that this got trained on reanalysis data, whereas the ENS system would initialize from real data and integrate forward. They are not exactly the same thing. So there is a little bit of artificial skill that we have to worry about, because when GenCast begins to make actual forecasts by taking the real-time data as opposed to reanalysis, then it will be a stricter test. Going forward, GenCast could be further improved for operational settings in several ways. GenCast operates at quarter-degree resolution, the current maximum resolution of the global reanalysis data. However, it may be useful to scale up to higher resolution to support additional applications and match the upgraded resolution of ENS as of mid-2023 at 0.1 degree resolution. In other words, the ENS system is still initializing the model at that resolution. Doesn't mean the data is that at that resolution. So GenCast, if it relies on data, then will it get global data at 0.1, or will it still begin to initialize with reanalysis being as current as now for integrating forward with this ML model. As a diffusion model, GenCast is computationally more expensive than an equivalent deterministic MLWP architecture because it requires multiple function evaluations to sample each forecast time step. To efficiently scale to higher resolution or to move towards computational parity with GenCast perturbed and similar models, distillation and other efficiency techniques should be explored. So some technical details there that I'll skip. Furthermore, previous work has shown that the performance of MLWP models that are trained on reanalysis can be further improved by fine-tuning using operational data such as HRES analysis inputs and targets. So here HRES analysis is again initializing with data assimilation and not reanalysis, which is a historic recreation of data with model integration. This underscores the importance of GenCast of traditional NWP-based data assimilation for providing training and initialization data. So those are details that I'm not being very strict with the explanation because those are technical details which is not my main goal here, just to give you a sense of where we are headed with MLWP for forecasts. Together, our results open a new front in weather forecasting, promising greater accuracy, efficiency, and accessibility across a wide range of settings. More generally, our work demonstrates that cutting-edge generative AI methods can capture very high dimensional and complex distributions over rich temporal dynamics with sufficient accuracy and reliability to support effective decision making in crucial applications. Essentially, the main message is that AI ML are now going to be part of the forecast business. And as I said before, even if we are using 1 kilometer dynamic model globally to make these forecasts, analyzing all that output to actually make products for users, whether it's Cyclone or anything else, is still going to need AI because it's going to be a big data problem when so much output is produced by a forecast model. So either way, we will find a blend of dynamics and AI, because dynamics is not going to be anytime dispensable in this sense, because AI is still taking past data and extrapolating to the future, and extrapolations are always tricky. So dynamics will guide somehow the forecasts. What the blend will look like, I'm not sure, but there may be literature on it that I will read to you once I find it. Okay, so let's leave this here for now.